The novel concept of Enfield splines that is introduced in our work combines higher order smoothness energies for rotational symmetry fields with the ability to pose hard constraints. Furthermore, we introduce a spectral reduction that enables real-time editing of such Enfield splines. These new concepts are put into practice in two applications: designing stroke directions for so-called hedging renderings, and designing ABRDFs to achieve complex but smooth highlight patterns. Let us illustrate the advantage of our higher order energies by the example of using hard constraints to place singularities.
With the common Dirichlet energy, we get a solution where the effect of the constraint is limited to the one ring around the vertex, and so it converges to a non-continuous solution under refinement of the mesh.
In contrast, the biharmonic energy used for our Enfield splines allows for such hard constraints and leads to a globally smooth solution. The Enfield splines remain consistent under refinement, converging to a spatially continuous solution. Another example that illustrates the necessity of higher order smoothness energies is local editing. Imposing alignment constraints has a global, sometimes undesired effect on the field. By adding boundary constraints, we enable local editing of the field.
In the presence of such boundary constraints, biharmonic smoothness energies are required to ensure a smooth transition of the field at the boundary.
We introduce a Fourier-like spectral reduction for Enfields, which enables real-time editing of Enfield splines. This means that we can slightly shift constraints and instantly visualize the result under these constraints. In the example shown here, we use this instant feedback to enforce alignment to features of the mesh which are not curvature aligned. The combination of real-time editing and hard constraints allows us to edit Enfields on highly detailed, high-resolution meshes on a small scale.
Here we show that interactive editing becomes prohibitive when working with more complex meshes. In the unreduced case, each solve requires half a second, and adding new constraints takes over 2 seconds. Applying our reduction allows for real-time frame rates independently of the mesh resolution.
The spectral reduction also allows us to change alignment parameters in real time. Hatching-based rendering is a visualization of a mesh by pencil strokes. As directions for the strokes, techniques often use principal curvature directions. However, it is often desirable to edit these directions to achieve higher quality renderings, as can be seen in the comparison here. Let us have a look at a live editing session of a stroke field. As can be seen, drawing hard constraints on the mesh leads to an immediate update of the field, and so the result can be instantly rendered, allowing for a feedback-based editing. Hard constraints offer a precise way of editing, which allows us to edit at a level of detail that would be impossible with soft alignment constraints. Since the Enfield splines are optimal solutions from linear systems, the results depend continuously on the constraints, which makes editing highly intuitive. In our second application, we use our framework to design anisotropic BRDFs on a mesh. This allows the user to intuitively manipulate the shape of highlights on objects. Since our fields are globally smooth, the highlights will have a smooth shape even far away from the user-defined constraints. The ability to modify n-field splines in real time enables immediate feedback on the effects of the constraints on the shape of the highlights. In this example, we used unit length n-fields, which assures a constant intensity of the highlights, but at the same time does not allow the user to suppress the highlights close to singularities. Our framework can handle both unit n-fields and fields of varying length. The latter shown here on a more complex example. The field shown here is both modified by hard alignment constraints as well as soft curvature alignment.